All right. We've got ourselves some exponential growth and decay models, Newton's law cooling. That's going to be applicable to you guys if you're taking a pizza out of the oven and you don't want to burn the roof of your mouth. That's the worst. Then we've also got logistic growth and decay models. So just like how money can grow continuously with our APERT formula, right? Other natural phenomena can also have uninhibited growth or decay. Okay. So like you've bacteria with like division of cells where they're multiplying, radioactive substances, because, you know, we all know that stuff quite well. And even population of like rabbits, birds, whatever, you name it. All these things can be modeled in different ways. So for the first one, law of uninhibited growth or decay, it's going to look very much like our APERT formula for continuous for compounding continuously interest. I said that in a weird order. Whatever. All right. So A of t, the amount after a certain amount of time, is equal to A sub naught, which is A sub naught is our initial value, or our initial population. And then it's E to the K T. We use K for the rate when we're dealing with these particular models. Okay. Now, another one, uninhibited growth, is going to be basically the same formula, except we're going to use N naught. You might see it written this way anyways. E to the K T. And since it's growth, K is going to be positive. Cool. So we'll have where N naught is our initial number of cells. And then K is a positive constant that represents the growth rate of cells. Lovely. All right, K is greater than 0. It's positive. If we're talking about growth, that makes sense. Positive number. Lovely. Lovely. All right, for our first question here, we have a colony of bacteria grows according to the law of uninhibited growth, according to the function N of t is equal to 100 e to the 0.045 t, where N is measured in grams and T is measured in days. So not quite as exciting as money, I know, but still very cool because we can model it with math. All right. Determine the initial amount of bacteria. So questions like these are great practice for the SAT. A lot of times they don't even have you do math in the math section. They just start asking questions about formulas. Well, our initial amount of bacteria would be the 100. Lovely. I like it. I like it. So now let's see here. We got, what is the growth rate of bacteria? And actually we should probably use some, we got grams here. So this should be grams. Sorry. All right. What is the growth rate of bacteria? Well, my rate is that KT. So that would be, 0. K is equal to, that's a terrible K. 0.045 would be my growth rate, which we could convert into a percentage where we could have 4.5% growth rate. Lovely. Now, what is the population after 5 days? Well, now I need to get my calculator out. So we'll have N of 5 is equal to, and then we're just going to go ahead and plug in 5 for T. E raised to the 0.045. Substitute 5 in. I have already actually calculated this. It is, and we'll go with squigglies, because we're going to be rounding, 125.232 grams. You'll see us use 3 decimal places frequently in these. But of course, we aren't rounding along the way because, yo-ro, you only round once. We'll be storing numbers again, much like some of the other applications we did. So how long will it take the population to reach 140 grams? So now we're asking how much time? Well, that would be, we got to set up an equation here. We're going to have 140 is equal to 100 e to the 0.045 t. We don't know t this time. So I'm going to divide by 100 to help us solve for t. All right, we're gonna sip some tea here on how much time. I don't know what I'm saying. All right, moving on. So if I divide here, I'm gonna have what 1.4 is equal to e raised to the 0.045 t. Now I can rearrange it. It'd be log base e of 1.4 is equal to 0.045 t. Now in my calculator, I can just use the natural log, right? So I can type in natural log of 1.4, and I'm going to divide all that by 0.045. So what I'm typing in my calculator is going to look something like this. Natural log of 1.4 divided by 0.045. And once again, I have this jotted down. So I've got it all. We have 7.477 days. Units are wonderful. So 7.477 days for it to reach 140 grams. Nice. Now the next one is, what is the doubling time for the population? What the heck does that mean? What does the doubling time mean? And I'm going to change colors here because we might get a little mixed in with the other work there. I have this feeling. So doubling times means, well, how long did it take for the bacteria to double? Well, what is double the initial population? Well, remember our initial amount of bacteria was 100 grams. So now I'll set this equal to 200 grams and I'm going to solve for t. So it's going to be the same exact process as before, just some different numbers from the previous part. I was trying to get that 5 to look a little nicer. There we go. It's a little better. A little squiggly, though. So divide by 100 to get 2 is equal to e to the 0.045 t. So I'd have log base e of 2, or just natural log of 2, is equal to 0.045 t. Divide by 0.045. And I get t is equal to, I'm going to be rounding, so I'm going to squiggly it up. Where do I have it in my work? We got 15.403 days. So that is our doubling time. It takes 15.403 days to double. Beautiful. If you're not getting those things, double check that you're typing it in correctly. Ask questions in class, all good things. Wonderful. All right, so we got another fun little colony of bacteria. You're going to know all sorts of things about bacteria by the end of this. You'll be like, whoa, we got to wipe up that mess. Otherwise, the bacteria will set in and double, and I could calculate it. Maybe you do want to do that. Maybe you want to leave a mess. Don't leave a mess. All right. A colony of bacteria increases according to the law of uninhibited growth. That's a fun word to say, uninhibited. Your math skills are going to be uninhibited, I'll tell you what. According to the formula on the previous page, if n is the number of bacteria in the culture and t is the time in hours, then n of t is equal to n naught e to the kt. I'm about to sneeze. I'm going to pause. That was a good sneeze. Thanks for hanging out. All right. If 10,000 bacteria are present initially and the number of bacteria doubles in 5 hours, how many bacteria will there be in 24 hours? Now, I feel like simply thinking about it, you're like, okay, 5 hours to double, 5 goes into 24 about 5 times, so 50,000, right? Something like that. Except when the bacteria is growing, then those new cells are now doubling themselves, so it's not quite as simple. It's not some linear model. It's exponential. What's up? Exponential, if you couldn't hear me. All right. So let's see here. How do we approach this problem? It doubles in 5 hours, meaning in 5 hours, there's going to be 20,000 bacteria. Perhaps we can set it up like the previous problem, the doubling time, and figure that out. So let's see here. We got 20,000 is equal to 10,000 e to the, we don't know k, but we do know that it took 5 hours to get there. So we knew the doubling time. We just don't know the rate, which is k. So now what we can do is we can solve for k the same way we solve for t. It's in the exponent, so it's going to work out the same mathematically. We'll divide by 10,000 to be left with 2 is equal to e to the 5k, I'll put. And then we'll have what? Natural log of 2 is equal to 5k. Don't forget, it's log base e of 2, so I just write it as natural log of 2. And then I can divide by 5, and we're going to get k equals, I got it written down, let me find it. It is 0.1386, but that is rounded. And do we want to round along the way? 0.1386. I don't believe I want to round along the way, children. Hashtag YORO. So I'm going to bust out my TI-84 emulator. All right, so as you can see here, I typed in natural log of 2 divided by 5, and I'm going to store this. All right, this is my K value. So what do you think I'm going to store this as? Which letter of the alphabet? Perhaps I will use K, because that just makes sense to me, right? It's the K value, and if I can choose something to store it as, why not make sense, right? Okay, cool. Well, I hit enter, but it's not letting me hit enter. Come on, there we go. Now the calculator is working. All right. So I've got my K values stored. Now I can continue along my merry way. So let's do that. So it says, how many bacteria will there be in 24 hours? Well, now I'm trying to find N, and I'll switch colors here since we're in a new gear of this one. I'll go with, I'm going to go blue. Okay. I was searching around. So how much after 24 hours? Not 25. 24 hours here. Okay. Well, that would mean that my initial amount is still 10,000. And then it's E raised to the K, which is 0.1386, but I'm going to use that K value. And then 24 goes in for T. Sorry, that got kind of crunched there. So let's plug that into our calculator. Let me bring that bad boy back up, and type some things in. So I got 10,000. There we go. And then E raised to the, I can just go ahead and hit alpha, K, and then 24. I'm going to put multiplication. I don't know why. It just seems weird to me. It wouldn't matter, but I still want to put multiplication there. All right. I think we got it all checked out. That looks good to me. Boom. We got 278,576.18 bacteria. Cool. So let's write that down. Luckily, I have it written down elsewhere because I don't remember all the numbers. 278, 576. It's a cool 7 there. 0.180. And that would be, we're saying bacteria. Nice. Okay. Now it says how long until there are 5,000 bacteria. And this is obviously we're using the same bacteria population, right? Same problem. So we can use the K from before. Oh, that's great. It's already stored. So we have 500,000 is equal to 10,000. E raised to the KT. So we got 0.1386 T. I'll put the number there so I remember that I'm solving for T at this point, but remember, we're going to use K in our calculator. So we'll divide by 10,000 on each side. And then I've got, what, 50? Equals, I always love doing this. I'm going to cancel all the zeros. That's so fun. That was like the best when you learned that back in like grade school. You're like, you can just cancel the zeros when you're dividing. That's awesome. Yeah, it was super cool, right? I know, you were as pumped as I was, right? Okay. Boom. Now I'm going to rewrite it in log form so that I can solve for the exponent because the logs are exponents. They help us solve for exponents. Beautiful. Log base E of 50. So natural log of 50 is equal to 0.1386 T, and then I can divide by that. Remember, that's my K value, so I'm going to use the K in my calculator that I've stored. Coming in so handy here, coming in clutch, as they might say. Let's pull that bad boy up. So I have natural log of 50 divided by, and then alpha K, enter. Beautiful. I wonder what would have happened, actually. Let's just see, just for fun. If I were to have divided by that rounded value, I wonder how much different it would have been. Oops, not 0. 1386. 0.86. So if I had to use this one, what would I have had? Not too different, really, in this one. Not like our other one where we had the investing and it took like an extra year and a half. Like, that's a big deal. So this one wasn't crazy different, but still we want to use that storing feature. Not only is it easier and saves time typing it in, it's also more accurate, right? That's a win, I believe. I can't remember how many wins I had there. Okay. So now, let's go ahead and jot that down. T is going to take, I've got it written over here on my other computer, 28.219. And that's hours in this one, right? Because that's our units. Yep. Hours. Wonderful. Nice. Good work there, children. That's some good stuff. I think we can just keep going here. We keep rolling. All right. So now we're going to focus on the decay aspect of it. It's the same formula, just now K is less than 0. So we'd have A naught E raised to the KT, where A naught is our initial amount. All right. And then we have K is going to be a negative number. That represents the rate of decay. Okay. So on to this lovely one. But before that, let's see here. We got all radioactive substances, this is our note here, have a specific half-life, which is the time required for half of the radioactive substances to decay. You may have heard that in some science classes before, right? It's kind of like the doubling time, but it's the decay version, right? So it's just half the population. And we'll work with that here momentarily. So, iodine 131, I'm sure you've heard of it, is a radioactive material that decays according to the function A of T is equal to A naught E raised to the negative 0.087 T, where A naught is the initial amount present and A is the amount present at time T in days. So A of T, A. Assume that the scientist initially has a sample of 200 grams of iodine 131, which, of course, we all know iodine 131, right? What is the decay rate of the iodine 131? Well, my decay rate is 0.087 decay rate, or you could say 8.7%. Okay, decay rate. Just make sure you have the percent if you're doing a percent, and do not put a percent here because it's not a percent, right? That's a decimal written as a percent. So why did I not use a negative? Well, we're saying decay rate, right? We're already saying that it's going down, right? So having a negative and a negative makes a positive. We don't want to do that. So since we say 8.7% decay rate, we're saying it's decreasing at a rate of 8.7%. It's saying it's going down. Don't add an extra negative, okay? Two negatives make a positive. We don't want that. How much iodine 131 is left after 5 days? Well, let's go ahead and plug it in. So he starts with 200 grams. So we have A of 5, right? This is in days, which is nice. We don't have to do any unit conversions. He starts with 200 grams. And then we have E raised to the negative 0.087, and just substitute in 5 for T. And when we do that, see, I got to jot it down here. Once we plug that into our calculator, we have 129.453 grams once you jot that into your calculator. Cool. I like it. Wonderful. Fantastic. Okay. Now it says, when will 100 grams of iodine be left? That's going to be our half-life, right? Well, let's see here. Same kind of idea. We're just dealing with different numbers. 100 is equal to 200 E raised to the negative 0.087 T. We're solving for T now. I'm going to divide by 200. So I get 1/2 or 0.5. So let's see here. 1/2 is equal to E raised to the negative 0.087 T. And then I'm going to throw this into log form, right? I'm going to rearrange it or rewrite it in log form so it can help us solve for exponents because logs are exponents. I'm going to keep saying that until you just keep saying, anytime you see logs, you're like, logs, exponents, logs, exponents, logs, exponents. They follow the same properties. Maybe I should add a property question here soon. So I have log base E of 1/2, or I could just write natural log. So I'm going sideways math. I've never been a fan of that, but it's what I got to do. Natural log of 1/2 is equal to negative 0.087t. And then we are going to go ahead and divide by negative 0.087 on both sides. And when I do that, what do I get for t? We end up with 7.967 days. Coolio. Nice stuff. Wonderful. Again, very similar mathematical process in all of these because they're all really like that APERT formula or look very much like it. So the solving is the same process. Awesome. Let's do a little Newton's Law of Cooling, and I think we'll cool it on this video. Alrighty, it's time for some Newton's Law of Cooling. Honestly, I think this one's the coolest one. No pun intended. Okay, pun intended. But it's like super applicable to our everyday life. If you're ever cooking food and you don't want to burn the roof of your mouth, right? You can math it up. You can really nerd it up to make sure you don't burn the roof of your mouth, burn your tongue by using Newton's Law of Cooling. I don't know how often we're going to be doing bacteria models and things like that in our everyday life, but I'll tell you what. This will work here. You don't have to just be like, and then test it and burn your mouth. You can just do Newton's Law of Cooling. There we go. All right. The temperature U of a heated object at a given time t can be modeled by the following function. I've already jotted in there to save a little time so I can make jokes instead. So capital T is the constant temp, right? So like the room temperature. U naught is the initial temperature of whatever you took out, whether it's a pizza, tacos, right? And then K is a negative constant. Okay, so let's go ahead. I'm going to jot this down once again so we have it. And there we are. So let's see here. Using Newton's Law of Cooling, an object is heated to 100 degrees Celsius, right? So that would be our, like when we take it out, that would be our U naught, and is then allowed to cool in a room whose air temperature is 30 degrees. There's our capital T, right? That is our constant temperature of the surrounding medium, and U naught is the initial temp. Perfect. Working out so far. Then it says, if the temperature of an object is 80 degrees after 5 minutes, when will its temperature be 50 degrees Celsius? So we're treating these, or similar kind of a question, just a different formula, to like when it's the bacteria grows to a certain amount or decays to a certain amount, when is it going to be this? Okay, that's the same idea here. So you're going to see some similar math, just a different, kind of uglier formula. Let's see here. So, we've got, see here, we said T is 30, right? I'm going to start plugging some things in. U naught is 100, and then we've got 30 again for T. E raised, we don't know what K is, but it's 80 degrees after 5 minutes. So if I said 80 and then, multiplied by 5 up here, that would allow me to solve for K, which is something we do each time, or not every time, but it's a common thing we've done. So now I've got everything numbers except for the K. Let's solve this thing for K. So if I subtract 30, I'll get 50 over here. In the parentheses, I'm going to have 70. So I'll have 70 E raised to the K times 5. This looks exactly like one of the other ones. Now that I've simplified, awesome. I'll divide by 70. That's a little better, 70. Not that great, though. And I'll get 5/7. So I'm going to zip on up here. So 5/7 is equal to E raised to the K times 5. And then, let's see here. We're going to have to do log form. Log base E of 5/7 or natural log of 5/7 is equal to K times 5. And we'll divide by 5. Perhaps we take out our TI-84s and pop that in there. Let's do it. We've got natural log of 5/7. It's kind of nice when it's natural log here, since, you know, my emulator doesn't have the log base feature. Ugh, it's such a drag. Cool. There we go. And we get this wonderful K value. That makes sense, right? It should be negative. Now I do want to store this. Oops, not alpha yet. My bad. Store. Got ahead of myself. Alpha. I'll store it as my K value. Hit enter. All right. Now it's in there. Back to this. So it wants to know when will its temperature be 50 degrees. I think I'm going to need a little more room, so I'm going to go ahead and zip over here. Let's see here. When is it going to be 50 degrees? So it'll be 50 is equal to, right? And then we're going to have 30 plus, was it 70? Because it was 100 minus 30, right? And then E raised to the K, whatever that is in my calculator. I'll just write K this time, and I'll write a note stored. And there we go. So we're just solving for T, right? I took U of T has become 50. The 30 has stayed the same. The 100 minus 30 stayed the same to be 70. E to the, now we know what K is. We're solving for T. So let's go about this algebraically. I'll subtract 30 and get 20 is equal to 70 E raised to the K T. Divide by 70, I get 2/7. All right. I know last time I wrote the K value in here, but I don't remember what it is. So I'm just going to say that it's stored. And then we have E raised to the K T. Remember, K is stored. I just said it. So we need log base E of 2/7 or natural log of 2/7 is equal to K times T. I'll divide by K. And then I'll get what T is. So let's find out what that's going to be. Let's see here. We've got natural log of 2/7 divided by, well, I've already got K stored in here, don't I? Wonderful. I mean, you could just type in those like 10 numbers there. Who's got time for that? I don't. I certainly don't. And here we get a nice, accurate answer this way. It's going to be 18.616. And that is in minutes. Just checking the units. We got minutes right here. Uh-oh. I can't write there because it's right by my camera. There we are. 18.616 minutes. Whew. I got worried there. Started freezing up on me a little bit, and I thought I was going to lose everything. Let's cross our fingers that doesn't happen. All right. So on over here, using a graphing utility, graph the relation found between the temperature and the time. Let's do that. But what is it that we're even plugging in now, come to think of it, right? Well, that'd be our U of T is equal to the initial, or the room temperature, excuse me, plus we need parentheses. We have the initial temperature minus the room temperature multiplied by E raised to the K T. And remember, K is stored. All right, so let's plug that into the TI-84. All righty, and there we have it. We have 30 plus 70 times E raised to the K T. T is our X, though, remember, and when we're plugging it in the calculator. So I'm going to hit, let's hit zoom standard and see what happens. We're not going to probably see anything here because it's the standard. But let's think about what we could do to adjust this thing. Or how about a zoom fit? Let's try zoom fit right now. Zoom 0. See what our calculator gives us. Not terrible. Not terrible. I'd like to make some adjustments, though. Let's think about our window here. I'm going to go ahead and let's see here. I'm going to head out a little bit further here. I mean, our other question was like 18 minutes. I'm going to go like 30 minutes here. Again, I like to think about this in terms of like what we're actually talking about, right? Our last answer was like 18 minutes. I don't want to stop at 10. And then our Y minimum, I would like to see, all the way down to when it's, maybe I'm going to go with like 0 just so I get that X-axis in there. And now let's see what it looks like here. And do I really care about, before time happened? No. So I'm just going to I'm going to go -2 just so I can see the axis. And I'm going to go, I think that's probably pretty good. Okay. Let's see what it looks like. Okay. I could dig that. So we can see it's eventually like starting to level out there and probably approach something. You know, probably getting to, perhaps room temperature. All right. So let's go ahead and graph that. And what number would that be right there? Well, that's going to be 100. The temperature it started out at time equals 0. So let's do a little graph here, a little graphy poo. I've got this. We've got 100. So that'd be 0, 100. Got a little curve to it. I like it. This would be our time axis in minutes. And then this would be temperature in degrees Celsius. All right. Right, because, you know, we know what Celsius is. You should know what Celsius is. I know, we use Fahrenheit, but the rest of the world uses Celsius. It's got nice numbers, right? 0 is freezing. 100 is boiling. Wow, those numbers make sense. We've got 32 degrees is freezing and 212 degrees is boiling because, you know, whatever. So in part C here, it says, using a graphing utility, verify the results from part A. So what was that amount we had? We had 18.616 for our t value. So if I do second calc and I do value and I plug 18.616, and again, this is, oops, forgot to put the decimal place. This is a rounded value, right? So it might be slightly off, but we wanted to know when was it going to cool down to what was the initial, or the question before it was, when was it going to be 50 degrees? Would you look at that? The Y value is 50.000191. Again, we rounded. So that checks out. That checks out. That tells us, yeah, hey, we're good to go there. Now, the next part, so check. That was a terrible check mark. I felt like it was going to be good the first time. Using a graphing utility to determine the elapsed time before the object is 35 degrees. Well, what could I do there to figure that out? How about I throw in a horizontal line of y equals 35, and then I can find the intersection, right? Because I can't calculate with a y value, so I use a second line in there to help out. So let's see here. I got graph. I'm gonna need to open up that window a little more. Get a nice breeze going. Oh, get it? Open the window a little more. Man, these are great. Good thing I had to do that. Otherwise I wouldn't have had time for that joke. All right. We can tell that it's getting a little long here with the video. I'm starting to lose it. All right. Looks like I saw it cross. I saw it pop back up. We're good to go. I'm going to hit second calc, and then I want to intersect, number 5. So if I hit enter, there's only one intersection point here, due to the behavior. It's not like we're dealing with a quadratic. So boom, there we go. 39.2165, 39.217, 39.217, and this is in minutes. All right. So I already alluded to this a little bit, but what do you notice about the temperature as time passes? Well, if I look at my graph, if I were to go to, say, a table, I think I have it set to ask. Maybe I need to do that real quick. Second table set, ask, okay. So I did already have that. Now, if I were to say, as my numbers get larger and larger, so let's say I go 40 minutes out, right? Because we've already dealt with some other stuff. We got 34. Let's go with 60 minutes out. And again, I'm looking at that Y1 column because the other one's just the 35. Okay, it's getting smaller yet. How about 100 minutes out? Because who's going to leave their food out for that long? Okay, 30.084. Let's go 200 minutes out. 30. Interesting. Perhaps I'm going to backtrack a little bit. 150. Let's find in the middle there. Okay, so I can kind of see, like, as it goes down, it's getting closer and closer to 30. I bet you if I plug in, like, 300, let's see if it goes below 30. It's not. Hint. Spoiler alert. There we go. It keeps saying 30. Now it's 30.0000 something. But what's happening is it's getting closer and closer to, as I said before, room temperature. All right. So closer and closer and closer to 30 degrees room temp. Which makes sense, right? It's never going to get colder than room temperature. That's crazy. It's just going to keep on getting closer and closer to room temperature. Our horizontal asymptote is equal to 30, not equal to, is y equals 30. And that makes sense in what we know about exponentials. If we look at our equation that we plugged into our calculator, 30 plus that exponential, so that 30, that's a vertical shift up 30, which is why our horizontal asymptote, which is usually y equals 0, went to 30. Y equals 30. Awesome. Well, that's plenty for this particular video. Hopefully the next one will be a little bit shorter, but we did cover a lot there. I appreciate you guys hanging out, and having fun here and using that calculator, using that store button with the K. That was awesome. America, freedom, rock and roll, Costco. Go Bears. Monday Night Football. Monday Night Football. Yeah, I'm doing this at 6:16. I think it's time to chill for the day. America, freedom, rock and roll, Costco. Bears.